Good morning. Today's Wednesday. Why should you go to a chemist for all your problems? Because they have all the solutions. Get it? Like a homogeneous mixture? That's a solution, and yes, it did click. Today I'm just going to show you, after we go over the homework, just show you how nuclear power works. And then you've got homework out of the Regents Review book. Looks like your test is going to be early next week. Okay, here we go. Half-life worksheet, evens. Some people are on the bus with this. Here are the answers to the one from yesterday, video from yesterday. I will post these as well. Some people are taking the number of days that they give you and dividing it by the half-life and then putting grams after that. That's not how you do it. That will tell you how many half-lives there are. Then you have to multiply that by half that many times. So, what is the total mass of radon-222 remaining in an original 160 gram sample of radon-222 after 19.1 days? Now I've got to look up my half-life in table N. So radon-222, it's 3.823 days. So 19.1 days. Whoops, 19.1 days. 3.823, I think it was. Unless it's 3238. What is it? 823, that was right. Okay. So just punch in your calculator. 19.1 divided by 3.823, and that's just about 5. That's the number of half-lives. So, an original 160 gram sample, so this is 160 grams, 5 half-lives, and each arrow is a half-life. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I start with 160. Half of that in 3.823 days. So 160 goes to 80. 80 goes to 40. 40 goes to 20. 20 goes to 10. And 10 goes to 5. Okay? This number happens, in this case, you got lucky if you said 5 grams because it turned out to be the same thing. But this number is the number of half-lives. Okay? Number 4. 6.2 hours, a 100 gram sample of silver 112 decays to 25 grams. What is the half-life of silver 112? Okay, so it tells me what the sample is. 100 grams. It decays to 25, so how many times do I have to do that? 100 to 50 to 25. This was all radioactive, this was half radioactive, this is a quarter radioactive. How many half-lives is that? 1, 2. Don't count the samples, count the arrows. Okay? So, if there were 2 half-lives over 6.2 hours, I just divide it then. 6.2 hours divided by 2. It's 3.1. So the answer is 3.1 hours. Does that make sense? That means 3.1 hours here and 3.1 hours. So 100 to 50 to 25 in 6.2 hours. So that does make sense. So my answer here is 3.1 hours. Number 6. If 3 grams of strontium-90 in a rock sample remained in 1999, approximately how many, that should say how many grams of strontium-90 were present in the original rock sample in 1943? So the first thing I have to do is find how many years it was between them. Quick math, 9 minus 3 is 6, so it's 56 years. 3 grams remained. Okay, so I have to look up strontium-90 in table N. Strontium-90, 29.1 years. So 56 divided by 29 is about 2. It's not very close, but it's about 2. So 2 half-lives. Okay, so 3 grams remained. So this is the end, right? When it says remain, there was 3 grams left. How many half-lives do I have? 2. So I have to go backwards this time. 6 to 3, that's a half-life. Here's my second half-life. This must be 12. So the original 12, there's half of this, and a quarter of that. So in 56 years, there were approximately 2 half-lives. So in the original sample in 1943, there were 12 grams. Okay? Last one. Number 8. A radioactive element has a half-life of 2 days. What fraction represents the amount of an original sample of this element remaining after 6 days? So, here's my original sample. I go through 2 days of it. It says 6 days. I need another 2 days. So now this is what it would be after 4 days. Now I've got 2, 4. There's my total of 6 days. Okay? So this is the original. That means it's 100%. So we would say it's a whole. It's 1. So after 2 days, it's half. After another 2 days, it's 1/4 of the original, half of a half, and 1/8 of the original, half of a quarter. Radioactive element has a half-life of 2 days. What fraction? 1/8. Okay? That's 3 half-lives. Hopefully you're getting better at these. I feel like we should have a conference call on these. Okay? All right, let me describe for you then, right now, what because yesterday we went through artificial transmutation. So essentially we're taking charged atoms and blasting them against atoms, up against atoms and through atoms that are not radioactive potentially. Okay, how does that work? Let's fill this in. Nuclear reactions. Energy released during nuclear reactions is much greater than energy released during chemical reactions. It's about 8,000 times greater. Energy released in a nuclear reaction comes from a fractional amount of mass. This is one to remember. Mass is converted into energy. Nuclear changes convert mass into energy, according to Einstein's famous equation, E equals mc squared, where E is energy, m is mass, and c is the speed of light squared. Okay? So nuclear fission and fusion we will learn about tomorrow. But let's look at how nuclear reactors work. First of all, go back a little bit. This is artificial transmutation. See this giant track here? This giant track is basically a more than a mile long tube that has particles moving in it. Okay? The particles are moving in there because they change, I should pull up an animation, they change the charge back and forth on this in order to get the speed going on it. So this, you put something like an alpha particle in here, and then you change the magnetism of it back and forth, so it goes around and around and around to the point where it's incredibly fast and it has a lot of momentum, and then they divert it, and then it hits something like a uranium atom, and then it will split it. So that's fission. Okay, that's nuclear fission. It's going to split it right apart, and huge amounts of energy are given off then. Okay, so what about a nuclear reactor? Now, we don't use, this is a natural type of thing. The other one I just showed you was artificial. This is natural. So this is naturally occurring radioactive materials, like uranium or plutonium, for example. Okay? So since these things gives off energy and it's surrounded by water, and the water gets heated up. And the water gets heated up to the point where it starts to boil. And when it boils, it produces steam. And you know that when steam, like if you're boiling a pot of water, the lid starts to come off because an increase in temperature is going to cause an increase in pressure. So this steam is under pressure. And then it starts to turn what's called a turbine. What's a turbine? Well, here's a turbine. Turbines are anything really that spin around an axis here. And you can, this would be inside of a windmill, for example, like a wind generating plant. This is the same type of turbine that is used in water, hydroelectric plants. So this basically has fans here, and when the steam comes in, it turns this. It turns it around. And here's the key. This copper-colored area here is copper. So they basically take copper wire and wrap it around a giant cylinder. And when they have that, they take giant magnets here and they surround the whole cylinder with magnets. So here is the cylinder, and it's covered with copper, and it's constantly spinning because it's attached to this. So the steam makes this spin. These magnets are stationary, so it's kind of like this. So when copper wire is spinning, going the opposite direction of a stationary magnet, that actually conducts electricity. It causes electricity to be made, okay, to be generated. So that's essentially how nuclear reactors work. Did you ever see one of these? I used to have one. It's a shake light. There's the copper cylinder, and inside there is a magnet. So when you shake that, electricity is generated, and then you can use that to light the light. That flashlight never needs a battery. They've gotten better with them. They were first pretty weak, but if you shake that, you won't need a battery ever. Okay? All right. Homework is Regents Review Book 225, 226 evens. Good luck.